All right, question 10 says, consider the curve described by the vector function r of t, which is 2 plus cosine ti plus 3 plus sine 2t j plus t k. Part A asks us to find parametric equations for the tangent line of this curve at the point when t is equal to pi over 2. Okay, so I want to describe a tangent line to the curve. Well, as we saw in the video on lines in R3, there's two key things I need to know to describe a line, right? I need to know a point on the line, and I need to know a direction vector for the line. Okay, so our job is to come up with those two things. Okay, so the first thing to note here, and I'll just, let's say this curve in red is the path of a particle being described by this vector function r of t, and in particular, right, at pi over 2, our position is, well, if I just plug in pi over 2 in for t, it'd be 2i plus 3j plus pi over 2k. Well, that then is really describing a point on our path. Okay, so in turn, since we're looking at this tangent line, that's going to give us a point on the tangent line. So the coordinates there are 2, 3, pi over 2, right? Those are just the components of our position vector. So that's good. So now how about a direction vector for the tangent line? Well, for that, right, we can use the velocity at pi over 2, right? Or in other words, the derivative vector, because we know that derivative vector points in the direction tangent to this red path. And so what's the derivative? Well, if we just differentiate component-wise, you get negative sine ti plus 2 cosine 2tj, don't forget the chain rule factor, plus k. If you plug in pi over 2 for t, you're going to get negative I, and then here you're going to get 2 cosine of twice pi over 2, right? So you're really going to get a cosine of pi, which is negative 1, so you get negative 2j, and then here get plus k. All right, so that is going to act as our direction vector, right? So we have our x0, y0, z0, right, from this point P0, and then we have our ABC from this direction vector. So we go ahead and put that all together. Our parametric equations for the tangent line then are x equals x0 plus at. So that's 2 plus a negative 1t. So 2 minus t, and then likewise y is 3 minus 2t, and z is pi over 2 plus t. And here I'm just indicating that there are no bounds on t. Okay, so that gives us a description of the tangent line to our path at the point when t is pi over 2. Now for part B, it says find the coordinates of the point where the tangent line in part A intersects the yz plane. Okay, so there's going to be some point where this line intersects the yz plane. Well, remember, the yz plane, right, is the set of all points in R3 where the x coordinate is 0. So what do I want to do to find this point of intersection? Well, I'm going to set the x coordinate of coming from our parametric equations, right, in part A for the line equal to 0. X is 2 minus t. So if I set that to 0, I get t equals 2. So that's telling us, right, that this green tangent line will intersect the yz plane when t is 0. So to find the other coordinates, just plug 2 in for t into the y and the z coordinates. And what do we get? Well, we get 0 for x, because we're, right, looking at the point of intersection with the yz plane. For y, you get 3 minus 4, so that's negative 1. And then for z, you get pi over 2 plus 2. And there you go. That's the point of intersection. And that does it for this video. Thanks so much.